In this video, we will look at the single source shortest path problem using greedy method, which is solved using Dijkstra's algorithm. The topic of single source shortest path is related to graphs, and graphs have many applications. For example, one such application is graphs can be used to represent a network of airports. In such a graph, the vertices represents the airports and the edges corresponds to available flights between airports. In this scenario, there are several possible cost metrics for edges of the graph. If we are interested in computing the travel time, then we use a weighted graph in which edges have cost representing the flying time between airports. If we are concerned with the airfare of a trip, then the cost of the edges represent the cost of a ticket. Finally, if we are interested in the actual distance traveled, then cost represents the distance between airports. So, if we are interested in traveling from New York to Los Angeles, we can use the graph to answer the following questions. What is the fastest time to get from New York to Los Angeles? Which route from New York to Los Angeles has the lowest cost of airfare? And what is the shortest possible distance traveled to get from New York to Los Angeles? Another example is graphs can be used to represent highway structures where vertices represent cities and edges represent highways. Each of these questions is a case of the same problem. Given a weighted directed graph G with set of vertices and set of edges with cost, the problem is to determine the shortest path from source vertex V to all the other vertices in the graph. So, we have to generate multiple paths and find the minimum length path. Therefore, this problem comes into category of optimization problem, and the optimization is based on the length of all the paths generated so far to be minimum. The greedy way to generate the shortest paths from source vertex to remaining vertices is to generate these paths in non-decreasing or increasing order of path length. This problem can be solved by greedy algorithm known as Dijkstra's algorithm. Dijkstra's algorithm is a greedy algorithm for solving the single source shortest path problem on a weighted graph in which the cost or the weights of all the edges are non-negative or positive. The Dijkstra's algorithm will not work on graphs which has negative cost on edges. The Dijkstra's algorithm finds the shortest path from the source vertex V to all the other vertices one by one. The essential feature of Dijkstra's algorithm is the order in which the paths are determined. The paths are discovered in the order of their weighted length, starting from the shortest and proceeding to the longest to find the path of minimum length. This is done using node relaxation technique. Let us look at how the minimum length paths are determined using node relaxation technique. Now, a path from any vertex V to vertex U is a sequence of one or more edges. For example, if vertex V is vertex 1 and vertex U is vertex 2, then there is a direct path from vertex 1 to vertex 2. Let's call this path as A. And the cost of this path is the cost of the edge between vertex 1 and vertex 2, which is 50. So, we say that the distance of vertex 2 from the source vertex 1 is 50. Then, there is also another path from vertex 1 to vertex 2 using an intermediate vertices 4 and 5. That is from vertex 1 to vertex 4, then from vertex 4 to vertex 5, and finally from vertex 5 to vertex 2. Let us call this path as path B. And the length of path B is the sum of the cost of the edges from vertex 1 to vertex 4, which is 10, plus the cost of the edge from vertex 4 to vertex 5, which is 15, plus the cost of the edge from vertex 5 to vertex 2, which is 20. Therefore, the length of the path B is 10 plus 15 plus 20, which is 45. So, we say that the distance of vertex 2 from the source vertex 1 using path B is 45. Therefore, the shortest distance from vertex 1 to vertex 2 is a path from vertex 1 to vertex 4, then from vertex 4 to vertex 5, and from vertex 5 to vertex 2, which is 45. So, we update the distance of vertex 2 from the source vertex 1 to 45. This updation is known as node relaxation. In general, the shortest distance or path from a vertex V to vertex U in a weighted graph is the minimum length of all the paths from U to V. So, we will apply the Dijkstra's algorithm to find the shortest path from the source vertex V to all the other vertices of this graph. This graph has 6 vertices and the cost of the edges are stored in cost adjacency matrix. The cost of I, j in cost adjacency matrix is the cost of the edge between vertex I and vertex j when vertex I is not equal to vertex j. The cost I, j in the cost adjacency matrix is 0 when vertex I is equal to vertex j, and the cost I, j in the cost adjacency matrix is infinity when there is no edge between vertex I and vertex j. So here we have the cost adjacency matrix with the cost of the edges from the graph. Let us consider vertex 1 as the source vertex V, and we will find the shortest path from the source vertex V, that is vertex 1, to all the other vertices of this graph. So initially the distance of vertex 1 to vertex 1 will be 0 since it is the source vertex. Then the distance of vertex 2 will be the cost of the edge from vertex 1 to vertex 2, which is 50. The distance of vertex 3 will be the cost of the edge from vertex 1 to vertex 3, which is 45. The distance of vertex 4 will be the cost of the edge from vertex 1 to vertex 4, which is 10. The distance of vertex 5 will be infinity since there is no edge between vertex 1 and vertex 5. And finally, the distance of vertex 6 will also be infinity since there is no edge between vertex 1 and vertex 6. So at this point, we have the initial distance of all the vertices from the source vertex V, which is vertex 1. Then the Dijkstra's algorithm maintains an array S of set of vertices. The set S will contain all the vertices whose shortest path have already been generated. Initially, all the vertices in set S are false because as of now, none of the shortest path for any vertex is generated. Then, since source vertex V is vertex 1 and for vertex 1, the shortest path is obviously 0 and there cannot be any other shortest path, therefore, the vertex 1 is assigned to set S by making S of 1 as true. Then, in the next step, we choose a vertex U whose distance is minimum and is not in set S. So, at this point, the minimum distance is 10 of vertex 4 and vertex 4 is not in set S because S of 4 is false. Therefore, vertex 4 becomes vertex U and is assigned to set S by making S of 4 as true. Now, we need to find all the vertices W adjacent to vertex U and not in set S. So, we have vertex 1 adjacent to vertex 4, but vertex 1 is in set S because S of 1 is true. Therefore, we do not consider vertex 1. Then, we have vertex 5 adjacent to vertex 4 and vertex 5 is not in set S since S of 5 is false. So, vertex 5 is considered for node relaxation to update the distance. The node relaxation is done by computing the distance of vertex W, which is the distance of vertex U plus the cost of the edge from vertex U to vertex W. So, the distance of vertex 5 is the distance of vertex 4 plus the cost of the edge between vertex 4 and vertex 5. The distance of vertex 4 is 10 plus the cost of the edge between vertex 4 and vertex 5 is 15. So, the distance of vertex 5 will be 10 plus 15, which is 25. Now, the new distance of vertex 5 is 25, which is smaller than the previous distance of vertex 5, which is infinity. So, we update the distance of vertex 5 to 25, and this is how node relaxation is done for vertex 5. Then there are no other vertices adjacent to vertex 4. So we move to the next step. In the next step, we choose a vertex u whose distance is minimum and is not in set S. So at this point, the minimum distance is 25 of vertex 5, and vertex 5 is not in set S because S of 5 is false. Therefore, vertex 5 becomes vertex u and is assigned to set S by making S of 5 as true. Now, we need to find all the vertices W adjacent to vertex u and not in set S. So, we have vertex 2 adjacent to vertex 5, and vertex 2 is not in set S since S of 2 is false. So, vertex 2 is considered for node relaxation to update the distance. The distance of vertex 2 is distance of vertex 5 plus the cost of the edge between vertex 5 and vertex 2. The distance of vertex 5 is 25 plus the cost of the edge between vertex 5 and vertex 2 is 20. So the distance of vertex 2 will be 25 plus 20, which is 45. Now the new distance of vertex 2 is 45, which is smaller than the previous distance of vertex 2, which is 50. So we update the distance of vertex 2 to 45, and this is how the node relaxation is done for vertex 2. Then we have vertex 3 adjacent to vertex 5, and vertex 3 is not in set S since S of 3 is false. So vertex 3 is considered for node relaxation to update the distance. The distance of vertex 3 is distance of vertex 5 plus the cost of the edge between vertex 5 and vertex 3. The distance of vertex 5 is 25 plus the cost of the edge between vertex 5 and vertex 3 is 35. So the distance of vertex 3 will be 25 plus 35, which is 60. Now the new distance of vertex 3 is 60, which is not smaller than the previous distance of vertex 3, which is 45. So we do not update the distance of vertex 3 since the previous distance 45 is smaller than the new distance 60, and node relaxation is not done for vertex 3. Then there are no other vertices adjacent to vertex 5. So we move to the next step. In the next step, we choose a vertex u whose distance is minimum and is not in set S. So at this point, the minimum distance is 45 of vertex 2 and vertex 3, and vertex 2 and vertex 3 are not in set S because S of 2 and S of 3 are false. Therefore, we can choose any vertex among vertex 2 or vertex 3. Let us choose vertex 2, and vertex 2 becomes vertex u and is assigned to set S by making S of 2 as true. Now we need to find all the vertices W adjacent to vertex u and not in set S. So we have vertex 3 adjacent to vertex 2, and vertex 3 is not in set S since S of 3 is false. So vertex 3 is considered for node relaxation to update the distance. The distance of vertex 3 is distance of vertex 2 plus the cost of the edge between vertex 2 and vertex 3. The distance of vertex 2 is 45 plus the cost of the edge between vertex 2 and vertex 3 is 10. So the distance of vertex 3 will be 45 plus 10, which is 55. Now the new distance of vertex 3 is 55, which is not smaller than the previous distance of vertex 3, which is 45. So we do not update the distance of vertex 3 since the previous distance of 45 is smaller than the new distance of 55, and node relaxation is not done for vertex 3. Then we have vertex 4 adjacent to vertex 2, but vertex 4 is in set S since S of 4 is true. Therefore, we do not consider vertex 4. Now there are no other vertices adjacent to vertex 2. So we move to the next step. In the next step, we choose a vertex u whose distance is minimum and is not in set S. So at this point, minimum distance is 45 of vertex 3, and vertex 3 is not in set S because S of 3 is false. Therefore, vertex 3 becomes vertex u and is assigned to set S by making S of 3 as true. Now we need to find all the vertices W adjacent to vertex U and not in set S. So we have vertex 5 adjacent to vertex 3, but vertex 5 is in set S since S of 5 is true. Therefore, we do not consider vertex 5. Then there are no other vertices adjacent to vertex 3, so we move to the next step. In the next step, we choose a vertex U whose distance is minimum and is not in set S. So at this point, only vertex left is vertex 6, and vertex 6 is not in set S because S of 6 is false. Therefore, vertex 6 becomes vertex U and is assigned to set S by making S of 6 as true. Now, we need to find all the vertices W adjacent to vertex U and not in set S. So, we have vertex 5 adjacent to vertex 6, but vertex 5 is in set S since S of 5 is true. Therefore, we do not consider vertex 5. Then, there are no other vertices adjacent to vertex 6. At this stage, we have explored all the vertices, and shortest path of all the vertices are computed from the source vertex V, which is stored in the distance array, and the Dijkstra's algorithm terminates. So, this is how we solve the single source shortest path problem using Dijkstra's algorithm. Let us look at the Dijkstra's algorithm. This algorithm is called shortest paths. This algorithm takes 4 parameters. The first parameter is V, which is the source vertex. The second parameter is cost, which is the cost adjacency matrix. The third parameter is the distance array, which will be storing the shortest paths, and the fourth parameter is N, that is the number of vertices in the graph. Then within the algorithm, we will first initialize the array S, which is the set of vertices, and the distance array. So we will have a for loop from I 1 to n, and within this for loop we will initialize all the elements of array S to false using the statement S of I assigned false. As well as we will initialize all the elements of distance array with their respective cost using the statement distance of I assigned cost of V and I within this for loop, where V is the source vertex. Then, since the source vertex is V and the distance of source vertex will be 0, so we will assign S of V as true, indicating that the source vertex is in set S, and assign distance of V as 0. Then we will have a for loop for each step of updating the distances of all the vertices from the source vertex. So we will have a for loop from 2 to n minus 1. Here we are starting the for loop from 2 because the source vertex V is already in set S, and there is no need to determine the distance of source vertex V. The for loop ends with n minus 1 since a path of n vertices needs at most n minus 1 edges. Then within this for loop we choose a vertex U from the vertices not in set S such that the distance of U is minimum. Then the chosen vertex U is assigned to set S using the statement S of U assigned true. Then for each vertex W adjacent to vertex U and not in set S, that is S of W equal to false, we will check if the distance of W is greater than the distance of U plus the cost of the edge between vertex U and vertex W. If this is true, we will update the distance of W by assigning the distance of U plus the cost of the edge between vertex U and vertex W. So this is the Dijkstra's algorithm for computing single source shortest path. Let us now analyze the complexity of the Dijkstra's algorithm. The algorithm starts with a for loop to initialize array S and distance array and will be executing for n times. Then we have a primitive statement which will be taking constant time, followed by another for loop which will be executing for n minus 2 times. Then the statement within the for loop to choose vertex U will execute for n times. But since this statement is within the for loop, it will execute for n squared times. As well as the for loop to update the distances will also execute for n times. But since this statement is within the for loop, so it will execute for n squared times. Hence, the overall time complexity of the Dijkstra's algorithm is O of n squared. So this is how the single source shortest path is computed using the Dijkstra's algorithm.